In this video we are going to talk about the two variable model and what are the various assumptions of the classical linear regression model. So this chapter talks about the two variable model and the hypothesis testing in the two variable model of regression. So what we did in previous video is that how the ordinary least square method works, how it works, and that is what we studied in our previous video, and we did an example of the SAT score in the last video, and from that OLS that we did there, we found out our equation of this SAT score example regression. So from that video we remember that our yi hat was our income and our xi was our score. So what we are going to talk about here is that since in the last video we talked about the OLS method. So under OLS method what we do is that we estimate our betas, beta 1 and beta 2. Okay, so beta 1 is this 432 and beta 2 is this, right? This we talked about in our last video, that how do we estimate these two things. Okay, so now moving ahead in this chapter, we are going to talk about the hypothesis testing, that is to know that how good our model actually is. Okay, so there we found out about our this beta 1 and beta 2. So now we want to know that how good is the estimated regression line that we have just estimated in here from a sample regression function. We want to know that how well it does fit to our population regression function, and how much of a good estimator is our sample regression function estimation. How good is the estimation of the sample regression function to the population regression function, that how much it represents the actual population from a sample that we had. So moving ahead, we here talk about that y is independent, as we saw in the previous video also, that y hat or yi's, not y hat, y, the income values are dependent on your xi's, right? No. Yeah, your income values are dependent on your xi's, that is your scores, है ना? Or was it opposite? Wait a minute. Oh, I did a mistake here. This xi is not score. This xi is our income and our yi is score. I have written it wrong here. I said it wrong also. So what happens is that our income, our scores are dependent on our incomes, right? What our scores are dependent on our income. Now what we get, what this statement means, that yi is dependent on this means from our equation yi beta 1 plus beta 2x plus mu. This was our equation, right? You can put I there, and okay, that doesn't matter in understanding. So what is happening here is that we have our xi values, we have our score values, right? We score values are given and errors are also there in the model, right? From these two we are estimating this yi value, our income value. That is what it means here, that yi is dependent on xi and ui. But with the theory part, what actually is that this is our scores, the scores of students will actually be dependent on your income, but we are given the scores already here. Now we have assumed that xi values are known or given. That is what I said here, that xi values are given, right? So what does the word given means here? That our xi values are not random, rather they are given to us, right? They are not random, they are given to us, and our ui, our error values are random, right? These error values are generated at random, and what the other word for random is stochastic. Now since we have this ui as our stochastic term, and we have our x as non-stochastic, and we are adding it with ui, which is a stochastic term, we are adding these two terms, what we will be generating is that our y will turn out to be a random term. Our income term will turn out to be a random term. Okay, our income term will turn out to be a random term. Y will become stochastic. So now we should understand the meaning of hypothesis testing at this point only, so that further when we move, we have a basic idea about what we are talking about in our subsequent lectures, that what hypothesis testing actually is. So what hypothesis testing means in this two variable case that we are studying here, that we are testing the relationship between our x's and our y's. Okay, we are testing the relationship between dependent variable and independent variable in form of our slope coefficients, betas that we get. So if I remember, here we had a beta 2, right, and there was also beta 1. So with these we test these betas, that how much of the significance or how much of the change is this beta explaining. What is the statistical significance of the betas? That is, the goal is to determine if the observed relationship, what is the relationship here? Relationship is beta. The goal is to determine if our observed relationship, that is our beta, between x and y is statistically significant. Okay, that is, if it is unlikely to occur by a chance. स्टैटिस्टिकली सिग्निफिकेंट का यहाँ पे मतलब है कि कहीं जो हमारा x एंड y के बीच में रिलेशनशिप है, that a relationship between x and y, it is not by chance, it is a theoretically explainable, it is a statistically explainable relationship between our x and y. That is what it means here. Okay, now moving ahead. So far we never talked about our this error term. Okay, what we said is that our error term is there, and because that error term is there in our this sample regression function, we add this error term to our model ui, so that we can get the exact values of yi. Okay, this we added there, right? इसके साथ हमारा बाकी का मॉडल था बीटा 1 प्लस बीटा 2 xi. This was our whole model. So when we talk about this this error term, now this error term is very important, as it has a very significant impact on our actual values that we are deriving from the regression. So what we do is that we make some assumptions about our error term, and this is precisely called the classical linear regression model. Now we are talking about the classical linear regression model and the assumptions of the classical linear regression model. So the very first assumption of the classical linear regression model is that it is linear in parameters. What does it mean? It means these linear in parameters. These beta 1 and beta 2, they have to be linear. Okay, we are not here concerned about the linearity of these two. Okay, we are only concerned about linearity of these two. यानी कि it could not be like this beta 2 square xi plus ui, or say beta 1 plus beta 2 upon beta 1 xi plus ui. Our model can't be like this in classical linear regression model. This is our first assumption. Okay, the second assumption is that your x values and your error values, okay, your x values and your error values are not correlated. That x is uncorrelated with the disturbance term. But however, if x variable is non-stochastic, that we talked about before, that our x is not random. If x is not random and its values are fixed, then this assumption is automatically fulfilled. Okay, this assumption is automatically fulfilled when our x values are not random. Why? Because our x values are not random, है ना, and our mu values are random. They are generated at random, so there cannot be a correlation between these two, right? So these two are automatically uncorrelated. So this assumption is fulfilled there only, right? This assumption also we talked about in the end of our previous video, the end of the second chapter that we did last time. So now the third assumption is that the expected value of error जो म्यू की एक्सपेक्टेड वैल्यू होगी दैट इज 0. एक्सपेक्टेड वैल्यू is to be written as expected value of mu given our x size. This is equal to 0. Expected value of mu given our xi is 0. Okay, moving ahead, here it has given a graph that shows this thing, that this what we just talked about, the assumption number and the second assumption, right, the third assumption. So that is represented by this graph here, that what our mean value of 0 means, and how it can be represented using a graph. Okay, that is shown here. It also says that with assumption 3.1 states is that these other factors or forces are not related to xi. What other factors and forces it is talking about? Those which are represented using the error terms, which are not included in the model. Okay, these are not related to the xi values and therefore given in the values of xi. Okay, and therefore given the values of xi, their mean value is 0. So it mean value given xi is 0. That is what is important from the conceptual point of view. Okay, so what three assumptions we have talked about until now, that are this thing is linear parameters are equation. Second, we talked about uncorrelated x and error term. Then we said that the expected value of error term is 0. Then fourth assumption, we talk about the variance of the error term. So we say that the variance of error term is constant. It does not change, right? What does this means? That we saw in this diagram above also that our variance was constant, right? All the graphs are like this. There is no where you will see that a graph like this, right, or a graph like this. So the variance of the values from the central tendency, are same across all the errors, right? All the errors, the variance is same. That is what it shows. Now this concept of variance being constant is called homoscedastic variance. This concept is called homoscedasticity, right? And when it is not constant, it is called heteroscedasticity or unequal variance. Okay, so that is what it is called. Now here is a graph showing that equal variance thing. See here, all of them have same variance, right? All of them have same variance. But when you see here, this is unequal variance case. The variance of all the different error terms is very different. They are not constant at all. This is what it means by having the constant variance or your homoscedastic variance, right? Now moving ahead, we talk about our fifth assumption, which is no autocorrelation. Now autocorrelation itself means that your error terms, say error term of this period and error term of the previous period, or error terms of two different sets, they are autocorrelated. They are correlated, sorry, not autocorrelated, they are correlated. When they are correlated, it means that there is autocorrelation, that is the previous values of your previous error values are impacting your current error values. Okay, your previous error values are impacting your current error values. This is the reason, so here we do not want this, and so we have the concept of no autocorrelation. That is, we assume that this thing does not happen. That is, our values are not correlated with its previous values. Okay, so means that having one error value above mean term will not imply that all the other error values are above the mean term. Do you get it? I'm saying that if we say that x is equal to 10 और हमारी एक error value आती है that mu is equal to 11, so it does not mean that all the error values will be like this only, that on the positive side only. It could be that the next error value is 9. Okay, so this implies that there is no autocorrelation, right? This also implies that our error terms are random, because if there is an autocorrelation, our randomness is lost. Then our error terms are not random anymore. That is the reason why we assume that our error terms are not autocorrelated. Moving ahead, what it says is that there is no systematic relationship between the two error terms and the another error term. That is what I have already said. Now, uh, because our error terms are uncorrelated, that is ui and uj are uncorrelated, and our x values are fixed, it will imply that our covariance of your yi and yj is also fixed. That is, it is also not autocorrelated. That is, we have assumed that there is no auto correlation in your UIs, right? It has implied no autocorrelation in YIs. We have written it here also that UI uncorrelated implies that YI is also uncorrelated. Now the another assumption here, I guess this is the last assumption. Yes, this is the last assumption. It says that there is no specification bias. There is no specification bias or specification error in the model. What does specification bias or specification error means? That we have missed a crucial variable. We have missed a crucial variable that could have impacted our model. Say if we talk about the demand and prices model, okay, so we say that our demand is y and our prices are, यहाँ पे हम डाल देते हैं pi instead of xi. Here we put beta 2 and beta 1 plus ui, right? This is a multiple regression model problem. Now if I take only prices, it will be a specification error because there are many other variables like taste, okay, like price of substitute or complementary goods. So all these things will also be impacting our demand here, right? So when we do not include all the other variables, it is a specification error. Now this has also given us an example here also, that if we are studying that the demand for a automobile and we include only prices of automobiles and consumers income, and we do not take into account the variables such as advertisement, financing cost, gasoline prices, that is petrol prices, then we are committing a specification error. So this is what specification error means. Okay, so rest of this we will do in our next video. That's it for this video. Thanks so much for watching.